All right, so a little bit more of chapter 1. All right, so batch learning is where you train it on all the training data and then just use it without doing any more training. And this is the most common one. This means that the performance will decay slowly over time because you trained up to a certain time and then the world changes. So you'll ask it about current events and it won't know about the current events. That's called model rot. So unless you keep retraining the model with up-to-date data, then it will gradually become irrelevant. Just like, a printed book. You print a book and it might be useful, but after a few years, it's out of date. So online learning will constantly train it on new data like stock prices, and you determine your learning rate. We'll play with this quite a bit in the projects. You have to choose the right learning rate. If you have a low learning rate, it's too slow to learn. If you have too high a learning rate, then it jumps over the optimum solution and sort of gets lost wandering around. So then you try to figure out how well does it generalize. You train it on data, and how well can it handle new data it's never seen before. This is the real test. So you can have instance-based learning. This is one type of learning where it learns all the training data by heart, and then it evaluates new data by deciding how close it is to one it's already memorized. This is one way to learn. I actually heard a psychology podcast from a guy that told me this is how he tried to learn physics. He nearly flunked out of physics because he would try to learn physics by memorizing everything in the textbook, and then when he had a test, he would try to figure out which problem is he asking and expect to see exactly the same problem he saw in the book. And it was more than halfway through the semester before he realized this will never work. You have to learn the method of physics and then apply it to the new problems, which I thought was obvious, but apparently not. People really tried to use this kind of learning, and that won't work for something like physics. So the other one is model-based. This is the one that works for physics. You have to make a model of it, like understand what F equals ma means and learn how to apply it. Then you can solve a whole bunch of things. You understand the mathematical model, and now you can apply your model to every instance and decide which side of this it's on. All right. So, for example, money and happiness. You can take some countries and rate how happy people are and how much money they make. And so you make a graph, and you see here's the red things of the graph. And so you could make a linear model. There's a trend. You see the more money people make, the happier they are. So it looks like putting a straight line through this data would be a pretty good fit. So you can try just two parameters like slope and intercept. And so this is a bad fit and that's a bad fit, but the blue line is a good fit. And you can measure the mean squared error. That's typically what you do. You take the distance between the prediction and the data and square it and add it up, and you try to make that number as low as possible. And that's fine. So that's called your utility function. Or cost function to determine how good or bad your fit is, and you optimize it, and then you'll find a nice straight line through the data that does a pretty good job of predicting it, which is fine. All right. But the challenges are, you might not have good data, you might not have enough data, your data might not really be representative of the population, you might have irrelevant information in the data that confuses your model, you might overfit or underfit. Overfitting is where you train too much to where you exactly spike every data point. So you're learning not only the trend of the underlying population, but also fitting the noise in the data. And so in general, by the way, there's a general rule. An underfitting is where you don't optimize it. So if I go back to this one here, underfitting would be having a bad fit like this, where you don't even get close to the data. Overfitting would be where you don't put a straight line, you actually make a complicated shape that jumps up and down to hit every data point. And therefore, it looks like you have a closer fit to the training data, but when you add test data from the same population that it hasn't seen before, it's not going to be a good fit of it. So, and we'll see that. And this is a problem with large language models. They are largely overtrained. The whole point of a large language model is it should have looked at all that data and learned how to write an English sentence or an English paragraph or page. It shouldn't have just memorized all that data. But the authors that wanted to see if they'd used their novels were able to put in like a paragraph from the novel, and it would then just repeat whole pages verbatim of the novel. That's a product of overtraining. It's repeating exactly the input data, and that's not what models are supposed to be doing. They're supposed to be learning the trend and not the details. And in some cases, they are apparently learning exactly, memorizing the input data. This has legal implications too. The lawsuits are saying the authors are saying you're simply memorizing, say, these New York Times articles and then repeating them back to people who ask without paying us royalties. And therefore, that's copyright infringement. And the model designers say, no, we're reading the articles the way a human would read the articles, and you put them up without a paywall so any human can read them, and the human doesn't memorize them and repeat them verbatim. The human just sort of learns what the meaning is and gets the gist of it. And that's the question. Putting a straight line through this is getting just the gist of it. Spiking every single point is just memorizing the input. And models do both to some extent, and the lawsuits are going to be arguing which of these is the legal consequences of what they've done. All right, and one thing that happens in general is if you have really a lot of data, then it doesn't matter exactly what kind of model you use. If you have enough data, that will pretty much overcome any deficiencies of your model, if your algorithm is not completely stupid. If your model, however, is non-representative, and that's what happened to us here, we included only this data, so we had this straight line, but if you actually go more widely in the world, you'll find these new red points that have a totally different relationship between happiness and income and show that you're fooling yourself. What you had was a small sample that appeared to show a trend, but the actual data out there in the world did not follow that trend. So your data misled you. This is, of course, a serious problem. And this happened when the internet was new. Around 1999, the internet came out, and certain companies like Yahoo started growing at an insane rate, like multiplying by a factor of 10 every year. And people thought, this is going to keep going up. And of course, it didn't keep going up. It went up for a while, and then it crashed. And so they had a simple prediction from a small amount of data, we're all going to get rich, rich, rich if this continues. But of course, it didn't continue. That's the problem if you have an unrepresentative sample. And then, of course, poor quality data. This is a big problem, and we'll go through it next time in detail. Your data often has errors, approximations, assumptions, and you're going to have to somehow deal with this. If your data is usually not perfect, and you have to clean it up before you can learn valuable things from it. So feature engineering is choosing good features to train on, where you decide which features are actually helping you get closer to the answer you want. And you may combine the features that the original person measured to create a feature that's more useful to you. And we'll do all that next time in considerable detail. Here's an example. This is what happened to Donald Trump. You may remember when the pandemic hit around 2020, Donald Trump was president. Maybe, I don't know when it was. He got in 2016. I think the pandemic hit in 2019 or something. Anyway, a few months into the pandemic, Donald Trump said, it's going to just vanish in a month. By Easter, it's going to fall to zero. Now, he didn't just make that up out of nothing. What happened is he had a person on his team who was a financial analyst, and they used Excel. And Excel has a curve-fitting feature. So they had some data about the number of cases over time of COVID, and the data had some noise in it. And look at this. Here's some data that's going up, but if you fit it with a high-order polynomial, like a 10th order polynomial, it will actually make predictions like this. This is what actually has the lowest mean squared error to fit it to like a 10th degree polynomial. And this is what his predictor did. He fit it in Excel with some polynomial, and it showed something like this. It's just going to fall to zero, like magic. And that's what Trump went with as a prediction. When a more sensible person would say, no, it's not going to fall to zero. The trend is rising. But if you just feed it into some kind of curve fitting without adding any human common sense to it, the curve fitting might choose high order polynomial and give you a stupid prediction like this. So this is called regularization, where you do not just try to find the model that has the lowest mathematical error, but you apply constraints. Like the model has to have some smoothness to it. You're not allowed to do crazy things like this right here. And that's part of every model. You add a regularization parameter so it is not just limited by fitting the data, it's also limited by some kind of restraint on how crazy it's allowed to get. And so here's overfitting the training data. We talked about it too. A linear model on all data would be this one, and a regularized linear model is the other one. You can decide what you want to do. In this case, of course, I would say none of these linear models are much good. You're really going to need something more complicated than a straight line to capture this data. Anyway, and underfitting is where you don't actually learn the underlying structure, so you need a more powerful model with more parameters or better data, or you need to lower your regularization. Your smoothing is too extreme, so you're limiting the available parameter values to ones that don't really capture the trend. So this is a problem. machine learning is not 100% done by the machines. As you can see, a lot of it is done by a human making judgments and adjustments to the data. So a machine does some of the learning, but you still have to have a human designing it. And so that's important to understand. And so we talked about this. All right. All right, so if your training set is too small or your data is not representative or too noisy or polluted, then you won't get a good model. And your model needs to be neither too simple, which is underfitting, nor too complex with overfitting. And there's not a mathematical way to decide that. It's a human judgment. When you decide how much of your data do you believe is actually the trend and how much of your data do you think is just the noise. And that's a human judgment you feed in. All right, so what you do is you split your data into a training set and a test set. Typically, you take 80% of the data for the training set and 20% for the test set. So you train it on the training set, and then you test it by feeding it the test set of data, which it has never seen before, and see how accurate it is. And that way you get a measurement of how good your model is actually learning the real trend of the underlying phenomenon. So this is called the generalization error. So if you feed it data it's never seen before and the model gets a lot worse, then you've done overfitting. You've memorized the training set, even the details of it that are not representative of the population. That's a generalization flaw. And so you have regularization hyperparameter to try to force it to smooth over the noise. And that's one way to do it. Another technique is cross-validation, which we'll do, where instead of having the training set and test set separate, you train it on like 2/3 of the data and test it on a third, and then you try different combinations of those thirds. So you just train it on different portions of the data. That's called cross-validation, is another way to do it. They're both ways to somehow make sure you're learning the real trend of the population and not just the noise of one particular set of samples. So another problem is non-representative data. So you can download, you want to train an iPhone app to recognize flowers. You can download flowers, but they weren't really taken with an iPhone. So they're going to be details of those images that aren't representative. So if you can get real pictures taken with the real phone you're going to use, then it would be better. And that's an issue. This is always an issue. The data you can get is never exactly what you want. And you have to decide whether it's good enough and whether you're going to spend money trying to get better data. So let's try another Kahoot, which is here. All right. All right. I guess this is it. All right. So which system memorizes each training image and then compares test samples by seeing how far away they are from the training images? Okay, that's called instance-based learning. And I don't believe I've ever used it. I don't think we have it in the projects, but it is one possible way to do it. All right, which system is best to stay up to date with changing data? Yeah, that's online. You keep feeding it new data online like stock prices so it can keep learning continuously or frequently. All right. Which one of these is a number that increases as the model gets better? Okay, that's the utility function. Measures how good your model is. The cost function is the opposite. It measures how bad your model is. So you minimize the cost or you maximize the utility. That's what your model does. All right, which of these is used to lower generalization error? All right, that's the hyperparameter, is the smoothing parameter that forces your model to capture the trend of the data, not the noise in the data. And that means it generalizes better. Now, if you show it new instances drawn from the same population, it will be more accurate on them because it was not misled by the vagaries of your sample. So that's hyperparameter. All right. All right. All right. Fair enough. So let me stop this recording.